Introducing my grandma, because that's a metaphor I keep using these days, Mike as well, similar to the Matrix, but more related to fluency, right? I would like my kids to do math like my grandma cooks. Now, I always tell this story. I'm sorry if you heard it before, but 3-4 years ago, I tried to record my grandma's recipes. How do you think that goes? Terrible. She doesn't know a single step. She just flows in the kitchen. She's, no, a little bit of this, a little bit of that. It's like, no, grandma, I know proportionality. Tell me the ingredients for one, and I'm the math guy in the family. I can do, like, if you give me the ingredients for one, I can do the numbers. She knows nothing. She just flows. No, a little bit of this, a little bit of that. If you don't have garlic, you can use. What happens to us millennials if we don't have garlic and the recipe in Instagram says garlic? We panic, we stop, and we Uber Eats, or we call our grandma, right, or our mom. So that's what happens with the kids, right? When they are learning math in the math matrix, right, they only do the tricks. So one day you change numbers for letters. That is the day. The day in 7th grade, 8th grade, depending on the state and country. But that day, the moment you introduce algebra, kids are like, wait. And you're like, but you know how to divide. Why don't you know how to divide polynomials if you understand what's division? Because I changed the ingredients. And if you only memorize your way out, if you just live in the matrix forever, it's very hard to be flexible as my grandma cooks. So our goal today is to develop a little bit this feeling of how can we help our kids to do math like my grandma cooks, which is almost like if they knew nothing, but it's quite the opposite. It's that they know everything. Right? All right, let's go. It's story time. Last time I did this experiment, I asked people to close their eyes, and some people was falling asleep, so please don't close your eyes. But I'm gonna read a real short text, and I'm probably not the best accent to read this, but let's be together on this, okay? I'm gonna read a text, it's not mine. At the end, I will tell you more. So picture the situation I'm describing. A musician is having a nightmare. In his dreams, he finds himself in a society where music education has been made compulsory. We're helping our students become more competitive in a world increasingly filled with sound, many teachers say. Since musicians are known for writing down their ideas in the form of scores, these strange black dots and lines must constitute the language of music. It is therefore imperative that students gain fluency, that's why we're here, in this language. It would be ridiculous to expect a child to sing a song or play an instrument without first having the proper foundations in theory and musical notation. Music class is where we take our stuff paper, the children say. We copy the notes from the board and make sure to fill in the note heads completely black. Once we had a problem with a chromatic scale and I got it right, but the teacher gave me a 0 because I had drawn some stems the wrong way, a kid says. In the upper grades, the pressure increases. Scales, models, and time signatures must be memorized for the exams. Singing a song, playing an instrument, composing an original piece are activities reserved for university or even for later. In the meantime, the children keep copying symbols in silence, never once hearing the music those symbols represent. Waking up in a cold sweat, the musician realizes that, thank heavens, it was all a wicked dream. How absurd, he reassures himself. No society would ever reduce such a beautiful and meaningful art as music to something so automatic and trivial. No culture would ever be so cruel to its children as to strip them from such a natural and fulfilling form of human expression. And yet, that is exactly what we do with mathematics. From that vision, right? But that's what we're doing. And with music, it sounds ridiculous. As I was reading, I saw your faces. It's like, that can't be. And yet, with mathematics, we are okay with that. But that's what traditional approach to mathematics does to our kids and our society. All right. This is the quote. We'll be sharing the slides later, so no need to take pictures. And now we're going to play a game. You know subitizing? Right? I'm going to display something. You have to recognize what it is. Right? You may know this example, but play along. It's going to be very fast. You ready? Yes. Okay, I'm going to get out of the middle. What was that? Trees. Trees. How much time did it take for you to see that those were trees? less than a second. And now if we go back and see, what do they have in common? Not much, right? The lower left tree, is that similar in any way to the upper left image? No, not the color, not the shape, right? Not even the angle in which this drawing is done. But still, your brain, I have good news, has a superpower. Because our human brains are very, 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 very fast at recognizing patterns, at recognizing structure, right? Actually, we're so good at that that sometimes we see faces where they are not faces, right? We see patterns where they are not. It's just that our brains are so ready to see patterns. It's like a superpower, I'm telling you, that we see them. Actually, we're so good at this that have you ever encountered these CAPTCHAs that say, click all the traffic lights or click all the bicycles? Right? That's hard. It's like, oh, is the post part of the traffic light? You ever encountered yourself? Like, why do I have to do this? Because you are much better than machines at recognizing patterns, at least until today. We'll see in a few years with AI, maybe this needs to change, this speech needs to change. But today, your brain, and the way IT people has to distinguish machines from humans is through making you see patterns. Because they know that anyone can do that, but computers, right? Isn't that like a superpower? Isn't that telling us that everyone is a math person? Everyone can see patterns. What are these? Same, right? We have several representations of the same. What are they? Fives? How do you know? Just counted or saw the pairs, right? Very good. Does the laser work? No, it's too far away. Anyway, so imagine, okay, yeah, these are all, are they all the representations of number 5? All the different representations of number 5? All the different decompositions of number 5? Which ones are we missing? Decompositions of number 5. So ways of expressing number 5. If we limit it to 2 addends, which ones are we missing? We have 0 and 4, 0 and 5, 5 and 0. What else? 4 and 1 and 1 and 4. 4 and 1, 1 and 4 at the corners. And then 3, 2, 2, 3. Could we say that we have them all? Unless we, I mean, of course, if we open the door to fractions, or yeah, then things change. But in the world of whole numbers, we're good? Now, this is a picture from our kindergarten program. The goal should be that at the end of kindergarten, every kid should be able to do this with any given number 1 to 10. And that's much more important than counting up to 1,000, right? That's the foundational skill, being able to decompose numbers 1 to 10. Why? Because imagine I ask you to solve 42 minus 5. What decomposition of number 5 is more convenient to subtract 5 from 42? 2 and 3, why? Right, so I'm breaking the 5 in first 2, I jump to the 40, and then, right? Of course, I can do it straight away, and as adults, yes, but as kids that are learning how to do mental math, having this flexibility, this decomposition at hand, really frees a lot of space in your brain so that your brain can focus. And that's what Fluency is about. It's about how can we liberate, free some space of our brain so our brain can focus in the actual challenge that we're facing. All right, so you said this, right? It's easier, or my 40 reference helps me have like a point in which I can like rest while I'm jumping, right? Even if it's just a metaphor of what your brain is doing, okay, 40, and then 3 more. It's very hard to do this unless you understand that 5 is 2 and 3. Yes? Now, integers. Lock the doors. Some people panic with integers. There's no need to panic. What can we do here? Okay, let's try to represent 5 in different ways. I'm telling you, these are 5s. You see? Why are they 5s? Why can I claim that they are all 5s? What property I'm relying on? One positive and one negative, what happens? We could agree that they cancel. We're okay with that as a class? Yes? Okay, if a positive and a negative cancel, we could say that 5 is represented here in 4 different forms. How many different ways of representing 5 would I have with this representation of chips? Can you imagine another one? A new one? Such as? Put me an example. Anyone? 10 greens and 5 yellows? Would that be 5? So how many different 5s could we find? Infinite amount of 5s. So can we build conceptual understanding on why this will be like if it was a positive through the different representations of 5? Let's see that. We have different 5s. If I want to do 5 minus 3, that's very convenient. This representation really works for me if I want to do 5 minus 3. But if I want to do 5 minus negative 3, it means that I need to take away 3 yellows. Where can I take 3 yellows from? And what is the answer? 8 positives. 8. So when you talk to math, math talks back. That's the structure that Mike was talking about, right? So how can we design activities, learning progressions, trajectories, sequences, so that kids build conceptual understanding? Now, some of you might be thinking, or out there you might find some people who think, yeah, but isn't much faster to say negative minus or minus negative, or in Spain we say menos por menos es más. Negative, negative, make a plus. And that's a rule. Yeah, it's easier, it's faster. Yeah, but that fades away if you don't remember the rule. You're relying only on memory. Now, am I saying that you cannot see the behavior and then learn, oh, yeah, it's like if the minus and the minus, you ever seen like this, whoop, and you can do that afterwards. That's okay. But first, we need to understand why. How many times in the math classroom, when you were students, you were like, I don't get why, but I'm just following, and I will memorize it. Spoiler, memory will fail you eventually. Some people, their memory fails to them in the next grade, after summer. Those are our struggles. Some people are luckier with memory and can survive. That's us, or grumpy parents, can survive in the system, can survive in the matrix, because they have good memory. But I'm telling you, even for those people, there's a moment in which the memory will fail. And then what? Unless you trained deductive skills, it's very hard to go back. But we're very lucky because mathematics is not a memoristic science. It's about deducing. So let's do it, right? That's what we're saying here. Now, a few quotes from mathematicians, because what we're saying about the structure is not just our opinion. It's what mathematicians describe as their jobs. You go outside and ask anyone on the street, what is mathematics? Their answer, you will see, by that answer, you will see if they are plugged in the matrix or not, right? Because the answer to what is mathematics is, if the answer is, oh yeah, adding, subtracting, doing calculation, you think mathematicians spend the whole day adding and subtracting? Absolutely not, right? So what do mathematicians do? Let's see, let's hear from them. Hardy, one of the best mathematicians in the past century. A mathematician, like a painter or a poet, is a maker of patterns. If our patterns are more permanent, it's because they are made with ideas. Beautiful quote. So, maker of patterns, seeing the structure, as Mike was saying. Kovalevskaya, the first woman that got accepted in a university to study math. It is impossible to be a mathematician without being a poet in the soul. Isn't that beautiful, right? Ian Stewart, he said, mathematics is the science of patterns, again, and nature makes use of every pattern that exists. So at the end, mathematics is the language in which the world is written, right? And last but not least, Paul Lockhart. Remember I told you that we would quote him again, the Californian mathematician. He's still alive and going strong. Doing mathematics should always mean finding patterns and crafting beautiful and meaningful explanations. So math is about structure and about patterns. So we have to provide the opportunities to the kids for them to see the structure and for them to deduce the properties and the rules. And we're going to see this today. Now, let's talk fluency for a moment. I'm not going that deep into this. This is like for another day. If you want to have us do a PD on fluency more specifically for more hours, we can go deeper into this. But just to remind you, which are the components of fluency, right? And actually in New Jersey, the standards changed a couple of years ago. Precisely, one of the main reasons the authors or the people at the Department of Education gave us to change the standards was to, instead of write fluently solve, fluently perform, operate, fluently add and subtract, they changed that to efficiently and flexibly solve, efficiently and flexibly add, efficiently and flexibly subtract. Why? Because according to them and what they explain in the official documents, many teachers were interpreting fluency as speed. So they changed that word to be more mindful on, hey, no, we don't mean speed, we mean efficiency and flexibility. And I would say also accuracy. You can be very flexible, very, very efficient, but if then you're wrong, I cannot say that you're fluent. Fluent also comes with, okay, but what, are we right? So here you have the components of fluency. Of course, one of our main reference for fluency, Jennifer Bay Williams. You can read her books and go deeper into this rabbit hole. And then Mike also in his session referenced fact fluency, computational fluency, procedural fluency. So I wanted to give like an overview on these 3 topics. And then after this, I promise, we go on to activities for the rest of the time that we have together. Yes? Deal? Okay, fact fluency, that's the core. Of course, if I am, let's say, in 1st grade as a kid, probably these times tables are not in my yellow zone of the brain. Not yet. Probably those are outside, right? If I am in 3rd grade, I'm learning multiplication. My teacher is trying to push things that are living here towards the yellow part. Does that make sense? Like, we're moving concepts in our brain to inner cores or inner circles of this diagram that we're going to complete now. So this is fact fluency. It depends on your age. You are expected to have some facts or more facts, right, in your brain. Then we have computational fluency, which includes the latter. But for instance, let's do this one. 48 plus 49. Turn and talk for like 30 seconds. How would you solve 48 plus 49? As you do it, think, what yellow facts are you moving around your head? Okay, as you try to solve 48 plus 49. The answer is 97. I don't care about the answer. I care about the strategy, right? So that's sometimes, you see that last week I was in a school and it was not in New Jersey, I have to confess, it was at the other side of the country in Seattle. And I was in this school and I am talking to this kid that was very frustrated because she didn't want to use the number line. She knew the algorithm, and she wanted to do only the algorithm, right? So the teacher comes to me and says, Albert, I have a hard time convincing this kid to use the number line. So I'm like, okay, let's, and I'm not a magician. I didn't change the mindset of the kid in one minute, but I had a very rich conversation with her because I sit next to her and say, so how is it going? And she said, I don't want to use the number line. And I'm like, okay, if my question was, what is the answer? Use whatever strategy you want. She was in 4th grade, right? So she didn't need to relearn the number line. But I'm not asking that. I'm not asking the answer. Actually, I will tell you the answer next time. I don't care about the answer in this particular moment. My goal is for you to represent, as Mike tried us to do today, my goal is for you to represent on the number line this particular operation and the jumps that we're performing. So I tried to shift my learning goal and be transparent with the kid in that matter, shift my learning goal and my focus to the strategy and the jumps and the representation. And that's the learning goal, and that's what you, as a kid, what you will be praised for, if that's what the kid was expecting, right? I am not interested in the answer. So now, that's why I'm doing this to you. The answer is 97. I don't care. What's the strategy? Anyone? Please.
I did
Okay. I'm going to revoice just for everyone in the room. 50 plus 50, and then back 3. Is 50 plus 50 yellow for you? Is 50 plus, do you need to calculate 50 per 50, or you just know? It's automatic. So that's what we're doing here. We're using something yellow, 50 plus 50, to, I'm not expecting anyone to have 48 plus 49 in the yellow area, but having it in the green area means that I can retrieve something from the yellow area so fast that I can have a flexible strategy or efficient strategy, right? About efficiency, it's also important that the time that we use, right? So I was in with this parent last year in a school, and the parent was like, I only want to teach the algorithm. Like, okay, 102 minus 99. And the guy says, it's 3. Like, can I see the algorithm you used? Oh, no, but in this case, no, I don't want to excuse it. I want to see the algorithm you used. No, but in this case, precisely. In this case, that's what makes you efficient, flexible. Nobody would call you fluent in mathematics if you need to use an algorithm to solve 102 minus 99. Call it whatever you want, not fluent. That's not fluent, right? And the standards are very clear on this, so it's not even a choice. It's not that we are here in a secret gathering like a cult deciding a hidden agenda. No, the standards in New Jersey are very, very clear. And you would be shocked out there asking teachers, what grade do you think that you are required by the standards to teach the algorithm? Many of us don't have this vision of what is the exact moment in which we are required to. We go by inertia because we live in the matrix, right? And the system is the matrix. So every time you have these kinds of conversations, go back to the standards, check, so that you can have more arguments when discussing with teachers, right? Or with other colleagues around when is the right moment to start introducing algorithms required by law. Okay.
Yeah, Albert.
Please.
The other thing that is very important is that when you said that 50 plus 50 was in the yellow part,
yeah.
We, as adults, can see that we remain 3, so we have to go back 3, but for them, for a child, is the fact fluence that is inside, is that he can split 10 in 8 plus 2, and 10 in 9 plus 1, and add these 2 and this 1 very fast. And for them, it's not so easy. And many times for the teacher or for the parents, it's like, oh, it's easy. But for them, it's like you have to do a lot of work in the yellow part with these small things. And we are not used to it as an adult, no?
Yeah, some students, when I was teaching at the university as well with Laura, and some kids came to our pre-service teachers came to us and said, oh, you're the ones that say that the times tables don't need to be memorized. I'm like, okay, how much time do you have? Because the nuance, the devil is in the details. I don't say that you don't need to know them by heart. What I'm saying is that memorizing is not the learning strategy. Memorizing is the outcome. Everyone at the end of 3rd grade should know by memory the times tables, yes, but not through memorization and repetition, right? But through learning and understanding why the times tables work. But that's why I'm reinforcing this. The yellow area is key, because what happens in middle school and high school, if not, is that you have kids there that are struggling solving an equation, but the problem is not the algebra or the equation. The problem is that they don't even remember what's 7 times 8. So they are struggling with that, and the brain is focused there while the brain should go somewhere else. That's the reason. And we reach the last layer of this onion, which is procedural fluency, right? And procedural fluency, I mean, we could add many things. It's almost everything in math, right? In number and operations should go here. But for instance, this combined operation here, I don't expect you to know this like that, like a fact. It's not yellow. It's not even green, but can you proceed and follow a procedure from a fluent perspective, right? So using computational and fact fluency, you see how the 3 layers pile up? And like maybe in 1st grade, I have a kid that to solve 10 plus 15 at the beginning of 1st grade, that's purple for them, because they have to use yellow facts that are like, for instance, 1, 2, 3, 4 counting. You see how our job in the fluency perspective is to move things to the yellow part, help kids mobilize concepts towards the yellow part. Yes? This diagram from Bay Williams helps me a lot to understand when I'm talking to a kid, okay, what is yellow, what is green, what is purple, and what is moving around, right? All right, the elephant in the room. Okay, Albert, we get it. Fluency, flexibility, but how do we develop the fluency? And this slide was done before listening to Mike's session. Now we have a few more strategies, so the elephant is not that important anymore. But still, when I reach this moment in my talks, it's like, yeah, okay, but now give me tools, right? So let's do it. That's why, I don't know if you realized in the program, the title of the session is The Solar System of Fluency. Let's dive into that metaphor, and we do activities together. This is the sun of the solar system. It's at the core. It's at the center. And this sun, many people think it's practice. Spoiler, it's not. It's conversation. What shines light to our planets that we will explore today is conversation. It's very unlikely that a kid alone, just because they are repeating, develops these more efficient strategies. The best way of democratizing the opportunities is to have a conversation so I can know how you did it and maybe learn from that. And maybe tomorrow you learn from me and so on and so forth, right? Conversation is at the center. So anything related with fluency needs to have a big piece of talking, sharing, right? Now, then we have two different types of planets orbiting this conversation sun. One planet is different strategies. It's almost impossible to be flexible and change the approach if I only have one approach. So by definition, if I only know one strategy, I cannot be fluent. Because fluency requires adapting the strategy, changing the strategy depending on the numbers and the moment, right? So different strategies is key. This requires 5, 6, 7 hours to explore the different strategies. Today, we're not exploring them, okay? But that could be part of another PD. Let's do an activity now. It's very similar to the ones Mike asked to you, so we're going to do it very, very fast. I just wanted to share these 5 steps, and I'm going to ask you, I'm not telling you the operation yet, because I want your attention. If I show you the operation, I lose you. So that's why what I learned is to blur the operation until I'm done talking. Otherwise, I lose you. So you will solve first alone, no talking. Once everyone in your table is ready, you will share your strategy with the group. Your goal, if you're lucky, that will be immediate. But if you're not, you will have to think a little more. Your goal is to find at least 4 different strategies, which is very doable because every table is at least 4 people, right? It doesn't mean that originally you had those 4 strategies. If you might be unlucky and everyone has the same strategy, then you will have to think 3 more. As a group, and this is the key part, order the strategies. There is no right or wrong. Your definition will be okay. Order the strategies in terms of efficiency. What do I mean by efficiency? It's like you don't waste resources. And one resource is time, yes. Another resource is paper. Another resource is maybe IT power, like battery of your calculator or of your phone, right? So discuss them in terms of efficiency, and then once you decided what is the most efficient, you will do another operation and test it to see if it works. Yes? Deal? This is the operation. 3.5 times 14. Let's do it. We'll give you 2 minutes. I know you're very excited, and it's just a multiplication. We're trying, just full transparency, we're trying to use the document camera so we can track what you say and write it down. As we wait, and it's more important for the next activity, I want to hear some strategies. Okay, let's list the strategies. Anyone wants to start? Please, thank you. Okay, standard algorithm, and that means. And what do you do with the comma or the decimal point in in the standard algorithm you learned. Because that's one thing. Standard algorithm might be different for her than for instance, for me, maybe, right? That I'm from another country. Yes? What do you do with a comma?
I just multiplied all the numbers and kind of like brought the decimal down one end from where the 0 was.
So you ignore the decimal point until you finish, and then you're like, okay, one decimal position, it's one decimal position. But why one, right? Another one. We have the algorithm. That's one. Oh, doubling and halving. What do you mean? Double 3.5, that's 7. Oh, we have 14 and that's 7. 7 times 7? 49. Oh, I love that. Oh. This strategy is very, very, very efficient in this case. The strategy is halving and doubling. So 3.5 is 7 if you double it. 14 is 7 if you have it. And you know that what you're just doing is compensating, right? El set sense ratlla, Laura. I la coma amb un punt. Ja, bueno.
Sorry.
Perdona, sí. Okay.
What do you want?
Laura is representing what you just said. We're not representing the algorithm. We all know imagine it, but we focus in this one. We're struggling with the European 7. You know that we crossed the 7, right? Okay. What else? That's one beautiful strategy. I think it's very, very efficient. You will have to work hard on other strategies to convince me that there's a strategy that is faster and more efficient than this one. Yes?
We broke apart, well, some of us, doing it by whole number, whether it was 14 times 3, or even if you needed to break that 14 further and do 10 times 3, 4 times 3, and then knowing half of 14 was the 7, adding that all up to get 49.
You see how many yellow things you're using and mobilizing to do that? You see why some of our kids struggle with that? Because we're asking them to mobilize many, many things at the same time. Yeah, that's a European one as well. It took me months to stop using the little thing and the 1. But the kids are not as kind as you. The kids are like, what is that? All right. Is it that a way of representing what you did? All right. We have 2 strategies plus the algorithm. 3 strategies. We need 1 more at least. Anyone else? Yes? Oh, area model, which is connected to this one because it's a visual of the decomposition. Yes. There's a thing also in this, when you do this kind of activities, sometimes the debate goes into if it's different or not as a strategy, but that's okay, right? Because then you're talking about the connections between these 2 representations, right? The 10, the 4, it's connected to the visuals. Any other strategy? Yes?
I drew it.
Oh, you drew it? What do you mean?
First grade teacher, so
Please.
10s and 1s.
Okay, so you used...
And then made it 10.
Also probably Mike's fault because we just did that example earlier and you were like conditioned by the representations, but that's beautiful. So you find a way of representing that, put it 3.5 times and see what happens.
But the beauty of that in the conversation is to talk about, yes, mathematically, we're all right.
Yes,
We go into efficiency.
exactly. That's a very good point. One thing is, okay, you're all right, I'm happy with every single strategy, even with the algorithm. Now, in terms of efficiency, let's rank them. Which one, in this case, is less efficient? And don't get me wrong, some people might think now, yeah, it might be the algorithm, but if I try anything that is not the algorithm, to me, it will be less efficient. That's okay. We can have a discussion on what is efficient to you, what is efficient to other ones. But as a classroom, we have to agree that in this particular case in which we can half and double, this one is pretty efficient. Of course, you have to see the structure. If you don't see the structure, that strategy is out of your reach. Yes?
Doing 3.5 14 times and adding it.
So it will be like that, but 3.5 plus 3.5 plus 3.5 plus 14 times. That wins in terms of less efficient. I love that. But it's important that if a kid says this is great because it's like the kid is understanding, I know you know, but playing the game, the kid is understanding that this is much less efficient. But we could do it this way. And that's the interesting conversation. Please.
I was thinking, though, in that quote, less efficient way, a student might see that 3 plus 5 is 3 plus 5 as the pattern of 7, I don't know.
And then you can connect to the half and double. So it's much more interesting and much more rich to ask these kind of tasks and do one operation, but in several different ways and talk about the properties and when and why, than A, B, C, D, E. Because if I ask you to do this kind of task or this kind of operation in a worksheet A to Z alone, it's very unlikely that you move from one strategy to another one. Very, very unlikely. Only happens in a few kids that are the kids that they don't even need a teacher. Those kids could do whatever on their own. Right? We all know those kids. What happens with the rest? Right? We have to put opportunities in front of them to have this conversation. That's why, but remember that I told you that the sun of this solar system is conversation, because unless you talked about the strategies, there's no way you become more efficient at the end of this activity. If you know how to multiply with the algorithm, and I make you practice, I make you hate math, because it's like again and again and again. Whereas through these kinds of tasks in which we foster more of the conversation, then the efficiency flourishes, the fluency is the natural outcome. Yes?
We could also have conversations on when context matters. Content can then change which one's more efficient.
Absolutely.
Like Laura, you might want to think in that area model.
If you're, exactly. And the context of sometimes the word problems or yes, that navigates your thinking 100%, yeah. And that fosters the connections that we want also to foster. And here is the last thing I say about this, and then we move on to another activity. The mathematical practices, Mike quoted a couple of them today, are standards. They are standards. I know you know, but we need to remind ourselves that, and outside of here as well, right? You cannot choose not to teach the mathematical practices. Now, how do you teach and develop the mathematical practices? Easier. Through a conversation in which you have argumentation, use of struct, or through a worksheet in which it's almost impossible that there is argumentation, connections. So it's not even a choice anymore. At least not in New Jersey, right? Very good. Oh, thank you for the change of screens. That was fast. Okay, I promise that earlier I had here, and if you saw this slide before, you know that here I had patterns, but Mike made me change it to use of regularity and structure. I like it because it's more like deeper. The matrix, I added this now, of course. I don't read Mike's mind. So the questions that Mike was talking about, will this always happen? And if yes, why? And if not, also why? And these are the questions that live in this zone of how conversation is shining this planet of regularity and structure. Without conversation, that planet is dark, right? And unless you're a very good explorer, an astronaut, it's very unlikely that you survive visiting alone that planet. All right, so now let's see another task in which we discuss about patterns and structure and rules. Okay, 5 to the power of 0. What is that? 1? Some people look confused, like, I don't remember. Yes, thank you, to proving my argument. You don't remember. Of course you don't remember if you just learned it as a rule. Now, how many, raise your hand if your teacher just told you, hey, any number to the power of 0 is 1. Move on. Right? We've been there. Now, the ones that are not raising their hands, I assume, is that the teacher tried or gave you an explanation on why. Right? So what we're going to see now is one of those beautiful explanations in which we will arrive to the conclusion. Right? So some kids, when I open this conversation after teaching powers, the kids say, it could be 0. Why do they say that? Because, and this is a very key thing that happens when you're teaching math this way, is that kids try to make connections and try to deduce, and sometimes their deduction process is wrong because they are using rules that worked in another realm, in this case, right, multiplication of whole numbers, and now they are applying that to a new thing that they are learning, and that can be a little mixed up at the beginning of the exploration. Fine, that's why you are there. It's not free exploration, it's guided exploration. You are there to say, okay, one hypothesis, one conjecture, if we're in math classroom, is 0. Another one, some kids told me, could be 5. You see why very fast that no, because 5 to the power of 1 is 5, and then y is 0 the same. It's weird, but I promise you, many kids say that it's this. Why? Because they are adding. Yes? You see the structure, that they are trying to make sense of this? And then, no one says the actual answer, which is 1. Because it's very counterintuitive for a 6th grader, 7th grader, to recognize why is it 1. And that's when most of our teachers, traditional teachers, said to us, hey, it's 1, it's something mathematicians agree on, move on. Wait, what? And sometimes that's the truth. It's true that some agreements are made among mathematicians. This is not one of them. This is not an agreement. This is a conclusion. It has to be 1, and we'll see why in a second. And it's probably, I put this image here because it's, do I give you the fish? Hey, any number to the power of 0 is 1. Eat the fish. And then if tomorrow you don't have fish, you starve. Now, instead of that, can I teach you how to fish? Can I go with you on the boat and teach you how to fish? Let's see that. 5 to the power of 4. We all know, remember, right? We have been working on this for 5 weeks now, classroom, that 5 times 5 times 5 times 5 can be condensed in a way that I can say, oh, it's 4 5s in a row. That means 5 to the power of 4. Yes? Now, what happens if I have 5 to the power of 3? I have 1 5 less. Yes? So in order to go, if I want to travel from 5 to the 4th to 5 to the 3rd, 5 cubed, what do I have to do? How do I go from this to this? I have to divide by 5. Yes? If it was addition, I would have to subtract. But since it's multiplication, I would have to divide by 5. Yes? So, and here is another property I'm not even talking about, which is subtracting 1 to the exponent is like dividing by the base. We just saw it. We deduced it. We can have another rule here. 5 squared? Yes? You know where this is going, no? 5 to the power of 1 is 5. And therefore, and not because I say so or because mathematicians agreed, but because math, when you ask a question, math answers back. You ask math, hey math, what happens if I go 1 more down? I have to divide by 5. Follow the pattern. See the structure. And what is 5 divided by 5? 1. It has to be 1. It's not because I said so. It's because it is. Right? So I don't know if this is I hope this is not the first time you see this deduction, but think of anything you know in mathematics that is arbitrary and convince yourself there is a way of building conceptually that. Even in high school, when many of us sometimes fall into more traditional things because things get bigger and we get overwhelmed. But there is a way of building every single idea in math. Because actually, how do I know that there's a way of building it? Because somebody built it before. Simple as that. All right, so we have building foundations in Fluency. Yes, we need different strategies to be flexible. We need to take always a look into the regularities and the structure. But how do we, imagine we build it, how do we consolidate? What other planets can we visit to consolidate? Let's see some of them. Don't laugh. Every time I show this in the American audience, some people laugh. Reproductive practice. I'm talking about reproducing, doing the same once and once again. Now, you might think, oh, Albert, how do you put this planet here? Aren't you against going to that planet? No. I'm against living in that planet. It's a very boring planet. From time to time, a visit might be worth. And with some kids specifically, from time to time, I might say, OK, now that you are a little better with the times tables, I'm going to put you some practice in front of you through an app or through some worksheets. That's OK. The problem is that traditional math was installed there forever. And that planet is very, very, there's no trees, there's nothing in that planet, right? Of course, all the trees are cut to print worksheets. So there is nothing in that planet. On the other hand, we have productive practice. Productive practice is similar in the sense that we have to practice a lot to to solve a given question, so the practice is there, but instead of just reproducing, we are trying to produce an answer. For instance, here is a 100 chart. What's the additive persistence? Does it ring a bell? What we've been doing with drop the whole morning? How many additions are you required to do, like if you were doing a worksheet? But that's the magic. You're tricked into producing an answer. In this case, what number has the largest persistence? Right? That's another planet, and we're gonna go and visit this planet. Here you have 2 sequences, so there's another activity for you. We have a few more minutes, so we're gonna do one activity more. I think we have time. Yes. Okay, these are 2 sequences. What I can promise to you is that both sequences follow the same procedure. Now I'm gonna give you 30 seconds. I don't expect anyone to see what's the pattern, but let's try to start seeing things. Don't feel the pressure. It's very unlikely that anyone discovers the pattern just at a glance. We're gonna tell you in a second, but we want you to start getting to know the numbers. And we put this example below, of course, because 19 and then 20, that's one reason. And second, because this looks very hopeful. Like, oh, I see some things, like, no. Abandon all hope. There's no hope. Since we're in a Star Wars theme today, right? With the planets and the... Okay.
And one interesting thing here is to analyze yourself. What are you thinking? Because sometimes when we have to see a pattern, like the example of the trees with Albert before, you just look and you expect to see the pattern. But here, if we look, it's like, okay, I cannot see anything. And sometimes our brains are like, okay, I will try with zooms. But I have a problem, but maybe it's a sum and a subtraction, but it's not working. And then I can say, okay, let's try with multiplications or divisions, but it's difficult in this case, but it's important to know how to do it. Because just to see and wait for the illumination, it's not a very good practice. So we have to teach also this to our students.
Yeah, what are the look-fors, right? How do you look for structure? It's not just hope. It's a pointed, a directed effort, right? That's what we call productive struggle. It pays off. Okay, Laura, what do you think? Can we review?
Anyone has seen anything? No? It was very difficult.
Rob, because he saw the next slide. No? You didn't? All right. There is a clue hidden, literally hidden, up there, right? But we'll see that. Okay. Here's what we're doing. Oh. Okay. What we're doing is 19, 1 squared plus 9 squared, that's 1 plus 81, 82. 1 plus 81. Now 82. 8 squared, 2 squared, 64 plus 4. 68. With your table, continue the 19 sequence and continue the 20 sequence and see what happens. Let's do it. This is to make you practice. It's just an excuse to make you practice. If we had a little more time, and it's entirely our fault that we don't have time because we get passionate, it's not yours. But if we had more time, we could now ask you for your answers. You can imagine how this part that we just skipped would go. But now let's see what is going on here, right? Everyone, I hope, reached after the confusion on what happens with 100 was clarified, which is very interesting. What happens when I have 3 digits, because that's not in the example. So I have to come up with the continuation of that rule, which is you take the digits and square them, 1, 0, 0 squared. Yes, as you can see up there. Did you notice that 19 reached 1 and then there was no point in continuing the investigation? Yes? Everyone? What happened with 20? Oh, you do it like this? What is that? The visual representation of the matrix. You live in a loop. So you think that everything is going well, and then you're like, oh, wait, this is escalating. And then it looks like, okay, 42, the answer to everything. 20. Who, when you saw the 20, who stopped and say, hey, wait a minute? Who did not stop and just, okay, 4? My team, just enthusiasts, right? You just keep going and then after a while. But here's the thing. If as a kid you notice, as a student, you notice, you deserve to stop because the pattern is saving you time. And that's what mathematicians do. You deserve that prize, that reward. If you did not, I'm sorry, but you deserve to do a few more. The activity adapts. That's one productive practice activity. What are you practicing here? Squares, right? Addition, right? Multiplication, following patterns, right? All that is there. But the purpose is not A, B, C, D, Z. It's an investigation. It's a mathematical investigation like mathematicians do.
And the important thing here is that these are two examples only to explain what are we doing. But this is the definition of happy numbers. So a number is happy when if
We
you
didn't
do,
make that up.
Yes, when you do all these things, you arrive to a 1. So in this example, we can see that 19 is a happy number, but 20 is not a happy number. Okay, so a very interesting investigation that we could do with our students is try to find all the happy numbers in the till 100, for example. And if I say this, wait, I will change. If I have the 100 numbers, one way to do it is, okay, we can split the numbers and say, okay, I will try it for 19, you will try it for 20, the other for 21, and do it without thinking, just doing. But if we think, what can we deduce? So, for example, tell me another number that for sure that is a happy number.
We know only so far 19 is happy. What other happy numbers can we know?
I look.
91. I heard 91, Laura.
Wait. This is a happy number, the 19.
Yes.
And 20 is not.
20 is not.
And which more?
Somebody said 91 right away.
Why 91 is not a happy number? Or yes?
I don't know.
And the yes? Okay, why?
Don't be shy.
Okay, perfect. You know, if 19 is a happy number, then 91 will be the happy number too. So directly, I have not to do anything. I just say that this is. And the number 2.
If 20 is not happy, neither is 2.
Okay.
But if you didn't see that pattern, I'm sorry, you do twice the job. But that's what you deserve in a good way. I say it in a good way. I promise.
Okay. Tell me another one that is not a happy number. Without doing anything, just looking your papers. The 4.
4 is not happy? How do you know that fast?
Because it's in the cycle of the 20. So we can say that, okay, 4 for sure that not, but.
What other numbers were in the cycle of 20, sorry.
So 40 isn't it.
40 out, what else? 16, and therefore 61 as well.
And 61.
What else? 37 and? What else? 58 and 85.
58.
42 and 24.
Okay.
It's kind of a pattern that I see like this, right?
Yes, we are making a connection. Now we have a symmetry.
We have a symmetry around the multiples of 11.
And these are special ones.
Yeah.
Yes, because the symmetry is.
The symmetry is a little broken because of the 0 and the 1s. Yeah.
Yes.
All right. Can we go back to the,
Yes,
or do you want to finish something here? Because
the
it's almost
important-
time.
Here. The important thing is that they skip practicing, just thinking and making the knowledge that you can make connections, no? And if you make connections with the symmetry and with the reverse of the numbers, and I see that in the cycle, all these numbers will not go to the number 1. So I can deduce a lot of things. I can skip practicing. And this is the mathematical part of the activities. And here you have all the happy numbers till 100. And another surprise is that, well, we are in February, but this year, if you check it, then you can check it at home with your family. But you can check that this year is a happy number. So
And again, we did not make this up. This is a property numbers app. And Albert, why is this important or interesting? It's a mathematical investigation, and then it's number theory, right? But the purpose is not that one. Just a few kids might get like inspired by that and become a mathematician. I don't expect every kid to become a mathematician, but at least they can be part of a mathematical investigation, which is completely professional in this case, right? All right, so there are more planets, and I'm sure we will discover others. It's okay. The important thing is that conversation needs to be at the sun, at the center, right? With Mike, we explored some routines. You could think of games, right? Actually, I was always too optimistic, and I had a final game we can do during lunch if someone wants. But this has been more or less all the talk. I just have a final message from someone very special. Thanks for listening, and it's lunchtime. Let's go. Thank you.